Hi everyone, this is Dr. Hopkins. I've got great news. We're going to cover buffers today. So we're going to start where we left off in the last video, where we ran a reaction where we had, at the end of the process of reacting weak acid with strong base, we had weak acid and conjugate base left over. So we'll start from that one where we had, I think, 0.167 molar acetic acid and 0.167 molar acetate ion left over. Of course, just to remind you, the Ka for that would be acetic acid going to acetate and H3O plus. We could set this up and do the ice table to figure out the pH using the Ka, once again, where we have our products of our reactants. Water doesn't count. And if we did this, and we're not going to do this in this video, if we ran through the ice table for this, we'd show that the X is small compared to 0.167. So that means it's small compared to the acetate concentration, and it's small compared to the acetic acid concentration. And if we plug those 0.167s into the Ka, we'd find that the Ka reduces to basically the H3O plus concentration, and in the end, the pH is 4.74 without doing the math. So let's do a little bit of additional math that I think is going to save you trouble in the end. So let's take the negative log of this Ka expression. So if we take the negative log of everything in that, so we did negative log of Ka, and then negative log of we've got acetate times H3O plus over acetic acid. So I've left the acetate over acetic acid in the first log, but remember, if we have products of logs, we can add them, because it's the property of logarithms. And so then we would have a negative log H3O plus, which looks very familiar to be kind of like pH. And that negative log Ka, we can just put the P in front of it, just like we did with pH. So it's pKa, which is the negative log of the Ka, is equal to the negative log of this ratio of our acetate to acetic acid plus pH. If we rearrange that to a form where we're solving for pH, that means the pH is the pKa of that particular, in this case, it's acetic acid, but the pKa of that acid plus the log of the conjugate base over the acid. And if we want to write that more generally to apply beyond just acetic acid, to apply to any weak acid, the pH is equal to the pKa plus the log of the concentration of the conjugate base over the concentration of acid in the solution. That's what we call the Henderson-Hasselbalch equation. And anytime you have, after you've done a reaction, you have concentrations of both weak acid and conjugate base that are linked together in an equilibrium, you don't have to do the ice table anymore. You can use Henderson-Hasselbalch to solve that. So let's do this math. Let's use Henderson-Hasselbalch to determine the pH when we're mixing 10 milliliters, so we're kind of sticking with the theme we had from the last video, 10 milliliters of 0.5 molar acetic acid and 7.5 milliliters of 0.5 molar sodium hydroxide. Here we have the problem set up where we have our acetic acid OH minus going to acetate. I've gone ahead and filled in, we had 10 milliliters of 0.5 molar, which is 5 times 10 to the minus 3 moles. It's been 5 times 10 to the minus 3 moles every time we've done it, the last 4 expressions. And then the 7.5 milliliters of 0.5 molar is 3.75 times 10 to the minus 3 moles of OH minus, which is the limiting reactant. So we would subtract that from each of those. So that one's going to be 0. We're going to end up with 3.75 times 10 to 3 moles of, that's 5, of acetate. So we would end up with 3.75 times 10 to the minus 3. And this is 1.25 times 10 to the minus 3 left over of acetic acid and acetate. Now, we could take those, and actually we will, if we want to figure out the concentration. We would divide, so this is 1.25 times 10 to the minus 3 moles. We have 17.5 milliliters, so that's 0.0175 liters. And I get that that is 0.071 molar is our acetic acid, concentration, and then our C2H3O2 minus our acetate is 0.2. Sorry, this is not. Let's erase this. So it's a little more readable. 0.214 molar. So we have our two concentrations. Now we could use the ice table and solve this, and it would work just fine. But we want to plug in our pH equals into the Henderson-Hasselbalch equation. So 1.8 times 10 to the minus 5. That's our pKa plus the log of the base, 0.214, over acid, 0.071. Okay, and so this, just to let you know, that pKa is 4.74, and then plus the log, I'm not going to solve this individually, over 0.071, it's actually the log of 3, which would be, finally, for our pH, 5.21. So you can see we saved a lot of time. Actually, if we did I went ahead and did this, but this is the pKa of acetic acid is always 4.74 if you remember the pKa's. And then we plug in our concentrations to the Henderson-Hasselbalch and we have the pH. Now, we know how to solve problems much easier for the pH if we have this mixture of a conjugate base and a weak acid. But the one thing we don't know yet, or we haven't talked about yet, is this idea, if we have a mixture of a conjugate base and acid, if we were to add an acid to it, there's base present to react with. If we add base to it, there's acid present to react with whatever we add. So mixtures of these weak acids conjugate base tend to be resistant to large changes in pH. And this is what we call a buffer. Buffer is a solution that's resistant to changes in pH. Now, we're not going to just accept that I say this is the case, this is a buffer, it's not going to change the pH if we add an acid or a base to it. So let's go ahead and do the math for this. So we're going to take our original, at the beginning, the 0.167 molar acetic acid, 0.167 molar acetate solution. It was a 15 milliliters and a pH of 4.74. We're going to add 1 milliliter of 0.1 molar HCl. We're going to figure out what happens to the pH. And then as a comparison, we're going to figure out what would happen to the pH if we added 1 milliliter of 0.1 molar HCl to an unbuffered, say just water, 15 milliliters of water. So let's do that math. All right, so now we have this problem set up. So we got 15 milliliters that contains both 0.16 molar, sorry, there should be M's here, and 0.16 molar acetate and acetic acid, each one of them. And then we are going to add 1 milliliter of 0.1 molar HCl. Now, we have an acid, a weak base, and a strong acid. The strong acid is going to react with the weak base. So we're going to set our reaction up as acetate plus our strong acid, dissociate. Remember, we're going to ignore the Cl minus. It's a spectator. So it's H3O plus. Now this is, remember, Kw draws this along. So this is an arrow giving us acetic acid and water, which we don't care about. Now I've plugged in the initial mole. So 15 milliliters converted to liters times 1.167 gives us 2.5 times 10 to the minus 3 of each of those two. And then 1 milliliter times 0.1 converted to liters, you get 1 times 10 to the minus 4 moles of H3O plus. So clearly the limiting reactant is our H3O plus, so we're left with 0 excess strong acid, which is good. And then we have 1.0 times 10 to the minus 4, so we subtract that. It reacts away that amount of base, so that's 2.4 times 10 to the minus 3, right? And then we're going to add, so it's going to generate 1.0 times 10 to the minus 4 moles of, acetic acid. So we get 2.6 times 10 to the minus 3 moles left over. So those are our moles. If we want to convert to concentration, so C2H3O2 minus, it's 2.4 times 10 to the minus 3 moles, divided by how many liters do we have? 25 milliliters, not 25, 16 milliliters. We did not add 10, we added 1. So 0.016 liters. And so that means this concentration is 0.15 molar. And I'm not going to write out all of the steps for the acetic acid, but its concentration would be 0.1625. I'm going to go ahead and carry the extra digit at this point, even though I know that's not significant. Okay, we have conjugate base and weak acid, so we can use the Henderson-Hasselbalch equation. So pH equals pKa plus the log of the base, C2H3O2 minus, over the acid, C2H3O2. And so that means this is 4.74. We remember that from before. I don't have to write it out. So the base is 0.15 over 0.1. Sorry, this is the log of 0.1625. And if we add that up, we end up with 4.71 as our pH. Notice, only changed 0.03 pH units. Okay, that's not a very large change in the pH. So that's what we mean when we talk about being a buffer. But why don't we go ahead and compare, like we said. So if we had just 1.0 milliliters of 0.1 molar HCl to 15 milliliters, so we're going to have a final volume of 16 milliliters. Now in this case, it's not going to react with anything. It's just adding to water. So this is a dilution problem. So this is M1V1 equals M2V2, everybody's favorite equation. So we have, we have 0.1 molar and then 1 milliliter equals M2 is what I want to know, and this is 16 milliliters. And so then if we do the math, this ends up being 625, I think it was, molar. And so then the pH, because that's the concentration, is 2.20 molar, just from adding 0.1 molar. So the 0.1 molar itself is a pH of 1. When we dilute it, it goes to a pH of 2.2. But it dropped from 7 to 2.2. So this is unbuffered. We added a little bit of strong acid and we got a large change in pH. Whereas when we added a little bit of strong acid to a buffer, we got almost no change in pH. And that's what a buffer does. And the last thing, we have the key takeaways from this video. So basically any solution that has conjugate base, and I should say a weak acid, you can use the Henderson-Hasselbalch equation to determine the pH. You don't have to use an ice table. And it's also true that those solutions are also considered, they are buffers, and they're resistant to changes in pH. So next time we will explore this concept of a buffer and why it's useful.